Hello and welcome back. Okay, we're going to do a series of 3 lessons that are going to explain the foundation of all quantitative research, basically. Quantitative research, data analytic methods. Okay, and the 3 lessons are on the normal distribution, the sampling distribution, and hypothesis testing. Okay, and so first we're going to start out with the normal distribution. All right. And basically if you can get a kind of a working understanding of these 3 lessons, the rest of quantitative analysis, data analysis is easy because it's just variations on a theme. All right. Okay, here we go. So I drew a little, I put a picture of a little bell there because the normal distribution is often called the bell curve. We're going to talk about what the normal distribution is, the history of it, and why we care, properties of the standard normal distribution, and a little bit on calculating z-scores and interpreting z-scores. The normal distribution is unimodal, symmetric. It has a bell shape. Why do we care about it? Many dependent variables are commonly assumed to be normally distributed. For example, math ability. Okay, we expect most people to fall into some kind of middle range of math ability, with some people being really good at math and some people being not very good at math at all, right? But most people will fall in some kind of middle range. All right. Um, we can use statistical techniques to make inferences about the values of variables that are normally distributed. It allows us, for example, to predict the frequency of times a score will fall in a particular range. If we know the distribution, we can make some predictions. Most basic statistical procedures assume that the values of the variables are normally distributed. um, are distributed in this kind of bell shape with most of the scores around some kind of mean and then some scores higher and some scores lower. Okay, now the history is kind of funny. Anyway, Abraham de Moivre was an 18th century statistician and he was a consultant to gamblers. He noticed that if you flip coins over and over and you graph how many times you get heads, an interesting pattern emerges. And if this little graph here at the bottom shows kind of what pattern emerges. Astronomers Laplace and Gauss saw a similar pattern if they graphed errors in the measurements of the stars and such. Their astronomical instruments were not 100% accurate. So if they graphed how far off they were, they could predict mathematically where a star was supposed to be. And if their instrument was showing them something different, they could graph how far off they were. They saw the same kind of shape, this bell shape. In fact, it's called a Gaussian distribution. For a while now, we call it a normal distribution. Quetelet and Galton applied the idea of normal and error to measurements of people. Okay, so originally it was just stars and things in the natural world. Okay, you could measure different features of animals, for example. You could use it for measuring things that occurred naturally, right? Um, but then let's try and apply this to people. It worked for stars, why not for people? They applied the idea of normal and error to measurements of people, which unfortunately contributed to the horrible and horrifying eugenics movement. So anyone who falls outside of what they saw as some kind of ideal range, um, then they are considered abnormal, and the eugenics movement led to the sterilization of many women of color and people with disabilities, and it was just horrible because it was basically scientifically justified racism, right? Okay, so there's that tarnished history, but we still get from it this idea of the normal distribution, and we use it. We still use it, right? The parameter for the normal distribution, and this is an idealized population focus. The parameters mu and sigma define the center, right? Mu being the mean and sigma being the standard deviation, define the center and the spread of the data. The problem is that there are different normal distributions, right? So we give a math test and there's one mean. We give a spelling test and there's a different mean. We give an English test and there's a different mean. That kind of thing. There are multiple. You could have many different normal distributions. You give one kind of math test and there's a mean at a certain place in your population. You give a test by a different publisher and there's a mean at a different place, and you look at the SAT math scores versus the ACT math scores. So there can be many distributions because there may be many different forms of a particular test or measurement, right? So for each different value, each different mean and spread, each different value of mu and sigma, we get a different normal distribution. And let's imagine that we're all on college admissions committees. Let's say we have one more slot in the freshman class of the college we're doing the admissions for. And let's say we look at one applicant where they have their SAT scores, another applicant has their ACT scores, and another applicant has their standardized test from their state exit exams, right? How do we compare? Okay. The solution to this problem is the standard normal distribution. Okay. Is standardizing. So you can imagine an IQ test with a mean of 100 and a standard deviation of 15 and a normal distribution. Okay. If we know the distribution is normal, if we know the mean and we know the standard deviation, then we know where scores fall. Okay, because 68% will score within of students will score within 15 points above or below the mean, or above or below 100. 68% of people will score within one standard deviation. Okay. Now, if we extend out to two standard deviations, 96% of all people will fall within 30 points of 100, will fall within this two standard deviation range. Okay. So if we knew, back to our previous example, if we knew the mean SAT score and the distribution of the SAT score, we would know kind of where the student is falling in the normal distribution. Same thing, we would know for this applicant where they were falling in the normal distribution if we knew the mean ACT and standard deviation of the ACT scores, and the same thing for the state standardized test scores. If we knew the mean and standard deviation of the state of whatever state standardized test that was, then we could know, because of the standard normal distribution, where the student is falling. Are they kind of in the top 2%, 16%, in the top half, or somewhere below the mean? So, this is a standard deviation trick, okay? As long as the distribution is symmetric and unimodal, as long as it's a normal distribution, we know um, where, if we know the mean and standard deviation, we know how many scores will fall within each interval. One standard deviation, two standard deviations, three standard deviations, and so on. How do we know? We know because some mathematician, when, somewhere, um, transform discovered that if you can transform the values to a standard normal distribution, you would get these. A standard normal distribution would get these percentages. Okay? It was proved mathematically. So we standardize values all the time. We do this automatically. We do this in our head. Um, So if I told you, one student scored 90 out of 100, another student scored 45 out of 50, another student scored 9 out of 10, we basically know these are all A's, right? They're all 90%. To be able to compare many such values, though, we need to put them on a common scale. So converting them to a percentage works, and that's what we normally do in our heads, right? Um, trans- Transforming a set of values to a standard normal distribution is what we do in statistics world. It's called standardizing. It's used a lot in measurement, okay? And it puts the measures on a common scale of standard deviation units. Okay, so now we're no longer in score. We're no longer, the unit is not how many points did the student earn. The unit is not um, what percent correct did the student get. The unit is um, how many standard deviations it was the student's score. How many standard deviations from the mean was the student's score. So basically, we're transforming our non-standard normal distributions, and there could be many of them, into a standard one with a mean of 0 and a standard deviation of 1. Okay? These new standardized values are called z-scores. That's what those are. Okay? These new values, that the values we took and we standardized them, they're called z-scores. The area under the curve, this curve, the area under it is 1, which is how we can calculate the percentages. Because if you have one bell-shaped one bell-shaped pizza pie, you cut off a part of it. You can, calculate what part of one that part that you cut off is. And you can guess that there's maybe some calculus involved in there, possibly. All right, so the area under the curve is 1, which makes it easy to calculate percentages, and we end up with what are called z-scores. So we're no longer the score of how many points correct, but these z-scores. Solving the formula indicates how many standard deviations from the mean a score is. So to calculate a z-score, we find the distance between the mean and the score, how many points the student earned, and then we determine how many standard deviations that is. The formula is the score, whatever score that student earned, minus the mean. Remember deviations, right? Um, that score minus the mean divided by the standard deviation. And that gives you the z-score. Mu is the mean of the population, and sigma is the standard deviation of those scores in that population. This is a simple linear transformation. It doesn't change the shape of the distribution. And it means the number of standard deviations above or below the mean. So let's talk about an example, okay? And this is kind of a little bit of a silly example, but you get the point. Dear Abby, you wrote in your column that a woman is pregnant for 266 days. Who said so? I carried my baby for 10 months and 5 days. I would have been a long pregnancy. Oh my goodness. My husband traveled to China for work, the baby could not have been conceived any other time because I only saw him once for an hour and I didn't see him again until the day after the baby was born. I don't drink, I don't run around, and there's no way the baby isn't his. So please print a retraction about the 266-day carrying time because I am in a lot of trouble. Signed, San Diego Reader. Okay. What's the probability of carrying a baby for 10 months and 5 days? Okay, according to well-documented data, gestation time, pregnancy time, follows a normal distribution with a mean of 266 days and a standard deviation of 16 days. Okay, so mu is 266 Sigma is 16. So if X is the gestation time, then what percent of babies have gestation times greater than 310 days, which would be 10 months and 5 days? We need to convert X equals to 310 into a standard Z-score. All right, so we do X 310 minus 266, which was the mean, divided by 16, and we get 2.75 standard deviations. Z equals 2.75 standard deviations. So if you had a statistics textbook lying around in the back, there would be a table showing Z-scores um, and so that you could find the corresponding percentage, okay? To find the area under the curve given a Z of whatever value. Okay, let's see. You would look on that table, Z equal to 2.75. You would look on the table till you found 2.75 for the score of Z. You would slide over. The distance from the mean to that Z would be 0.497. You would slide over. The area below that Z is 90.997. The area above is 0.003. If we were to convert 0.003 into a percentage, we slide that decimal point over 2, we get that there's only a 0.3% chance of a pregnancy lasting as long as 310 days. Only 0.3% chance. Okay? So less than 1 in 100 pregnancies are going to last that long. In fact, only 3 out of 1,000 pregnancies are going to last that long. I don't know. So this is the last slide in this lesson. What do you think? Is this San Diego reader telling the truth? There's only a 3 out of 1,000 chance. Now notice we're getting a chance, a probability. Okay, we're not saying for certain that that San Diego reader is lying. We're not saying that it's a lie. We're not saying it's completely impossible. We're just saying that's very, very unlikely. All right. You have a great day. Bye-bye.